In section 7.3, we come across our first real formula for probability. Now, of course, the first couple sections did have a formula for probability, but I just kind of called them not real formulas, right? Because in the end, they were more ideas about dividing big pictures and small pictures and that kind of thing. This formula is a little more formal, I suppose would be the best way to describe it, in the sense that we need to actually follow this specifically. It's not a general idea to keep in mind. And so what does this formula represent? You may recognize it. It looks very familiar. It looks sort of like the inclusion-exclusion principle, and it's definitely based off of that. In fact, you can think of the union as an OR event, and if you think back, that relates back to the definition of union. So remember, X is in A union B if X is in A or B. In probability, we can say the event A union B is the event that A or B or both happen. And so, of course, this is probability of A, probability of B, and then we subtract, because of double counting, the probability of A intersect B. Now, A intersect B can be thought of as the AND event, meaning both events occur at the same time. And then one thing that could happen is that you have mutually exclusive events. Also known as disjoint events. These type of events cannot occur at the same time, and what you will find in this case is that means the AND event, probability of A intersect B, is 0. So whenever this is true, this formula simplifies quite a bit. But really, in each problem, we want to think about that a little bit. So this is a formula you should memorize, you should know, and we're going to look at a couple of examples of how to use it. So in this first example, a lot of the work is done for us. It's really just arranging the information that we have. So it tells us an inspection of desks made at a furniture plant reveals that 2% have structural defects. So I'm going to write that down. So the probability of structural defects is equal to 0.02. And 3% have finished defects. So the probability of finished defects is equal to 0.03. And 1% have both. So the way you could think about that is that's the probability of structural defect and or intersect. A finished defect would be 0.01. It says find the probability the desk you randomly select has a structural or a finish defect. So this is asking for probability of SD or FD. So remember, OR is essentially the union. And applying the formula from just a minute ago, this is probability of SD plus probability of FD. So first event plus second event minus the third event, the intersection of the two. And so the reason I said this problem has a lot of the work done for us is because we already have these probabilities, right? So this would be 0.02 plus 0.03 minus 0.01. So we end up with 0.04. Of course, many of the problems we see won't be like this, but this is a good practice problem as far as just how to arrange the information, recognizing what you're reading. So always think about, you can think as percentages in a way as probabilities when random selection is occurring. So let's look at another one where maybe a little more is going on and we have to do a little bit more work. So in this case, we're told we have a group of 100. 28 have the first initial R and 11 have last initial R. Also, 6 have both. We're going to select a person at random, find the probability that the person has a first or last initial R. Okay, so probability first is R or the second is R. This time, instead of trying to interject the union and intersection notation, let's remember the intersection represents the AND event. And so we'll say here, this is the probability the first is R plus the probability the second is R minus the probability that both are R. In other words, first R and second R. Right? And that's just the formula. Probability the first plus probability the second minus probability the AND event. So probably the first initial is R. So we randomly select somebody from this group. 28 have first initial R. So this would be 28 out of 100. Okay. Second initials R. Well, it says 11 have last initial R, which is the same idea as second, since we're only looking at, we're assuming we're looking at 2. So this would be 11 out of 100. And then minus. Well, 6 have both. So this would be minus 6 out of 100. So 11 minus 6 is 5, right? So this would be 28 plus 5, 33, divided by 100, in other words, 0.33. So if you were randomly to select somebody from this group, there would be a 0.33 chance that that person would have two initials, first and last, as R. So this should really feel a lot like working with inclusion-exclusion, because essentially that's what we're doing. And in a way, the counting here has been done for us a little bit more than maybe we had to do in 7172, where maybe we had to use combinations and permutations, although this is still something that we'll have to deal with even in that setting. Something that's going to help us in that setting, though, is the idea of complementary events, and this is a very, very important idea. And it comes from the idea that if you know the complement, you can actually indirectly find the probability of the event. So let me explain what complement is. So this is how we write a complement. This is a complement. It represents everything in the sample space but outside of A. So if this is our sample space S and A is right here, the complement is everything out here, right? So it's just like with set theory. Now, how is this useful? Well, probability of S, the sample space, is equal to 1. And together, A complement and A make up the entire sample space. So together, their probability is 1. Solving this, we get a very useful formula, which you can see right here. So let's suppose that it's very difficult to find the probability of A, or maybe just it's annoying. It's not necessarily difficult, but it's complicated and it's not something we want to do. Well, that means that the probability of A complement is probably much easier or less annoying to find the probability of. So if we could find that probability instead, all we have to do is subtract it from 1, and we will indirectly have found the probability of the more difficult event A. So in some cases, that would be silly. They're about the same, but there are specific cases where it's very, very useful. And so I give you 3 cases here. In each of these, this is just practice for identifying when we're looking at a complement. What does the complement look like? So in the first one, it says, okay, we're going to flip a coin. A is the event, we get tails. So of course, A complement would be whatever's left over in the sample space that isn't tails. So you could probably guess that's heads, right? Okay, what about B? We randomly select a student. B is the event, we select a student under 20 years old. So what would B complement be? B complement is the event. We select a student. Now you're probably thinking older than 20, but don't forget, it's got to be everything in the sample space outside of what we picked. So under 20 versus 20 or older. So in both of these cases, I probably wouldn't bother with the complement. But the last one, C, I probably would. It says we randomly select a group of 5 students. C is the event at least 1 is a woman. So if I wanted to find the probability of C, at least 1 out of 5 is a woman, I would have to find the probability that the first person's woman, the rest are men. The second person, think about all the different ways you could have at least 1 woman. That means 1's a woman, the rest are men. Or 2 are women, the rest are men. Or 3 are women, the rest are men. Or 4 are women, the rest are men. Or 5 women. So I lost track, but that's several different things to count, right? Each one representing a different probability. And then with OR, we have to apply the OR formula. Well, the other approach would be to look at C complement. So think about all the things that represent at least 1's a woman. If at least 1's a woman, either 1's a woman or 2 or 3 or 4 or 5, right? So what's left out? The possibility that you select all men. So C complement is the event. We select all men. And this is where the complement is useful, approaching problems like that. So let's take a look at an example where the complement is helpful. So here I say to find 2 methods, because what I want to show you is why we use the complement. So a pen holder holds 20 pens, 5 of which don't write. We're going to select 3 pens randomly, find the probability at least 1 writes. Okay, we want to find probability at least 1 writes. Okay, so let's say we didn't want to use the complement. We didn't think of that. So method 1, no complement. All right, we got to think about all the ways this could happen. At least 1 writes. So we could have 1 writes and 2 don't. Or 2 write and 1 doesn't. or all three right. So we got to think of all three of these cases. Now they're each ors. That means we can add these probabilities, but we might have to select or subtract something. Now, we don't have to subtract something as long as the events are mutually exclusive, which they are. So we would only have to add. So for method 1, I say, okay, 1 writes, 2 don't, 2 write. I got to think of each of these. First, let's think about the sample space. We're selecting 3 pens randomly from 20 pens. And so order obviously doesn't matter. So the denominator for this is going to be 20, choose 3. Okay. Now for the numerator, it's going to have each of these. So let's think about the first case. 1 writes, 2 don't. Okay, if I pick 1 that writes, let's go ahead and figure this out. So 5 don't write, so 15 write. That will be helpful to have up here. So there are 15 ways I could pick that 1 that writes, and to pick the 2 that don't, I'd have to choose from the 5, so it'd be 5, choose 2. Okay, or, so I got to add 2 write. So I pick 2 from the 15 that write, and I pick 1 that doesn't, so that'd be times 5. Or I pick all 3 that write, so that would be out of the 15, I pick 3. All right, so that's a little bit of pain. It wasn't horrible, though. It would be really horrible if we were picking maybe 6 pens or something like that. So you could see this could go in a direction I don't want it to go. It could be pretty awful. But let's go ahead and calculate this. So for my numerator, again, that's 20, choose 3. I get 1140. So I'm going to go ahead and write that down. So 1140. So my denominator is 20, choose 3. And so for the numerator, it'd be 15 times 5, choose 2. Plus 5 times 15, choose 2. Plus 15, choose 3. I get 1130. Okay, so 1130 divided by 1140 is 9912. So a very likely event. And think about that. That makes sense. Most of the pens write. So if you just grab 3, most likely you'll get at least 1 that writes. Okay, let's try the second method. So let's say we didn't want to do all this work, or it was many more pens. Like, that amount of work is not going to happen if you're picking 5 or 6 pens. You're going to be having so many cases here, it's not worth it. So what I do is I recognize that the probability at least 1 writes is the complement of, so it's equal to 1 minus the probability. And so I say, okay, if at least 1 writes, that's all these cases. What's the left out case? That 3 don't write. So it's 1 minus probability you pick 3 that don't. So this would be 1 minus, okay, now I got to figure out this probability. Well, you're picking 3 pens out of 20. And then we want to know the probability of picking 3 that don't write. So you're picking, out of the 5 that don't write, you're picking 3. So this is 1 minus whatever that fraction is. And so that fraction, we already know the denominator is 1140. And so the numerator is 5, choose 3. So 5, and then I go to my probability function and do 3, and so I get 10. Now, as you can see, if you do the math real quick, you get the same thing. That's 1130 out of 1140. Double check if you would like, and you get the exact same value, I would say with a lot less work. This shows you the power of using the complement. I would highly advise to always use method 2 for these types of problems. This method has limits. It was doable with 3. It's not going to be doable with more. Well, it's going to be doable. It will just take you forever. Method 2 will always be very short. So complementary events are very powerful as far as helping me solve problems. And it all comes back to that idea of OR. The other method I couldn't do without OR. So let's take a look at another example. And this one you could apply to any number of coin flips if you wanted to. It says we're going to toss 4 coins. Find the probability tails comes up at least once. Okay, so probability tails at least once. If you wanted to do this direct using method 1 like I showed you a minute ago, you would be finding tails once, or tails twice, or tails 3 times, or tails 4 times. Very limited and very complicated. So instead what I'm going to do is do 1 minus the complement. So the complement to tails at least once would be all heads. Okay, so now I got to figure out how that would happen. So this would be equal to 1 minus. Okay, so the sample space, you're tossing 4 coins. And so I'm going to do some scratch work down here. So if I do 4 coins, 1, 2, 3, 4, how many possibilities are there for the first coin? There's 2, right? For the next one, there's 2. The next one, there's 2. So this would be 2 to the 4th. Okay, so my denominator up here is 2 to the 4th. And then we say, okay, how many ways could you get? Heads, 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 heads. And this may kind of feel confusing. There's only really one way that could happen. You get heads on the first, heads on the second, and heads on the third, and heads on the fourth. So there's only one way that could happen. And so this is actually 1 minus 1 over. And so you know this is 2 squared times 2 squared, right? So if this is 2 squared times 2 squared, this is 4 times 4. This is 16. So in other words, this result is 15 over 16. In other words, it's very likely you get 9375. And this would work no matter how many coins you wanted to look at. The main thing that would change would be this value right here. So again, this all with the complement, I'm able to do this very, very quickly. And we'll see some other methods that will actually really help with this type of problem later on, including independence of events.